Imagine you are tasked with fixing a tiny, seemingly harmless bug in a shopping cart feature late on a Friday afternoon.
Oh, the classic Friday deploy. We all know how that ends.
Right, it's a universal fear. You change one single line of code, you hit deploy, and suddenly the entire user authentication system just, well, it crashes.
Taking the whole application down with it.
Exactly. And you spend your entire weekend tracing the failure, only to discover that the shopping cart and the login system were secretly sharing the same database connection variable. Welcome to the absolute nightmare of tightly coupled code.
It really is a nightmare.
It is. Before we proceed, I must explicitly state at the beginning of this broadcast that this is an AI-generated analysis. Welcome. You are listening to a scripted, formal, and highly professional comprehensive analysis.
Very formal.
Yes, quite. Our mission today is to provide a detailed technical review of how to build scalable, maintainable systems. We are going to translate complex architectural concepts into clear, accessible English for you, our listeners.
And our source material for this analysis is the fantastic book Clean Architecture with .NET by Casey Crouse and Steve Smith.
To understand why clean architecture even matters, just consider that tangled knot of electrical wires that represents legacy code. If you pull on one single wire to fix a minor feature, you risk, unplugging the entire system.
Which is exactly what happened in your Friday afternoon scenario.
Exactly. Clean architecture provides a methodology for organizing those wires into safe, distinct, and isolated panels.
Right, and to understand how to avoid that deployment disaster, we really must analyze the specific structural failures of tightly coupled code. The authors actually illustrate this using a common shopping cart scenario.
Oh, I remember that part. It's a great example.
Yeah, in a poorly designed application, the user interface routing, the complex business logic, and the direct database access, they're all just blended together.
Right, into a single controller class that often spans, over 1,000 lines of code?
Easily over 1,000 lines. And that causes severe cognitive overload for the developer. But honestly, the structural horrors are even worse.
How so?
Well, the example application uses direct SQL queries that are constructed through basic string concatenation.
Oh, wow, so just pasting variables directly into the query string.
Exactly. This means if a user types malicious code into a search box, the application directly executes it. It creates a critical SQL injection vulnerability right there.
That is terrifying. And didn't they also mention something about hard-coded file paths?
Yes, they did. The code contains hard-coded Windows file paths for saving log files. So if your operations team attempts to deploy this application in a modern Linux container,
It's going to crash immediately.
instantly, it crashes upon writing its first log entry because the file system structure is fundamentally different in Linux.
It's just so fragile. But, developers recognized these pain points long ago, which led to a natural evolution in software design. We didn't arrive at clean architecture overnight.
No, not at all. It took years of trial and error.
Right. The industry first moved to N-tier architecture, which organizes code into horizontal layers, kind of like a cake. You typically have a presentation layer on top, a business layer in the middle, and a database layer at the bottom.
Which was a step in the right direction.
It was, but in N-tier, the business layer still depends heavily on the database layer beneath it. If the database changes, the business rules often break.
Yeah, the coupling is still there, just shifted downward.
Exactly. So to solve this, developers introduced onion and hexagonal architectures. And these models, they actually flip the dependency structure entirely.
Right, they place the business logic at the absolute center of everything.
Yes, and they treat everything else, including the database, as just an external plugin. And this evolution basically culminates in Uncle Bob Martin's clean architecture, which is governed by what he calls the dependency rule.
Ah, the dependency rule. That is the core of it all.
It really is. It dictates that source code dependencies can only point inward. The inner layers must know absolutely nothing about the outer layers.
Right, and the center of this architecture is composed of very specific, distinct components. At the absolute core, we have entities, which hold the core domain data and the strictest business rules.
Okay, so the entities are the most protected part.
Exactly. And surrounding them are the use cases, which orchestrate specific business workflows, like checking out that shopping cart we talked about.
Got it. And where do interfaces fit into this?
Well, we utilize interfaces as essentially contracts. They define what actions the application needs to perform, but without specifying how they are executed.
So they just say what needs to happen, not the implementation detail.
Exactly. And finally, we have gateways, which reside in the outer rings. They handle the actual communication with external systems like sending an email or saving to a database.
Right. And because the dependencies point inward, the core use cases rely only on interfaces, never on the external gateways themselves.
You got it. That's the secret to decoupling the system.
Okay, wait, hold on. Let me just play devil's advocate for a second. If we step back and look at this logically, introducing all these layers, all these interfaces, and strict boundaries, it sounds incredibly time consuming.
It definitely adds upfront complexity.
Right. I have to ask, aren't we just over engineering here? If I am building a straightforward, inventory tracker, aren't we just undoing all our productivity by spending hours building abstract layers before we even write a functional feature? There must be scenarios where clean architecture is objectively the wrong choice.
Well, the architectural overhead is a known factor, and you have highlighted a very valid concern. Clean architecture is fundamentally unsuited for very small applications, fast proofs of concept, or simple apps where the primary function is merely creating, reading, updating, and deleting database records.
So basically standard CRU'd apps.
Exactly. When a system is essentially just a spreadsheet with a web interface, layering introduces completely unnecessary friction. Furthermore, it is generally avoided in real-time, ultra-low latency systems.
Like high-frequency financial trading platform.
Precisely. In those environments, passing data through multiple architectural layers and mapping between different objects, it introduces microscopic performance delays. And those delays can cost millions of dollars.
Oh, wow. Yeah, that makes perfect sense.
But for enterprise systems that must adapt to changing business requirements, new technologies, and rotating teams of developers over the course of 10 or 15 years, in those cases, isolating the core logic pays massive dividends in long-term maintainability.
Okay, that clarifies things. Let us examine how this translates to a practical .NET environment. According to the development lifecycle outlined in the source text, developers must adopt what they call an inside-out mindset.
Which is very different from how most of us learn to code.
It is. Instead of starting by designing database tables, which is how many developers are trained, we must start at the very center of the system.
Right. Building from the inside out means scaffolding the application entirely independent of the infrastructure. In the .NET implementation for Project Odyssey, which is the fictional e-commerce application in our source material, the most critical decision is splitting the central logic into two distinct class libraries.
The domain project and the application project, right?
Exactly. The domain project is strictly reserved for core business rules and entities. Meanwhile, the application project sits just outside the domain and is responsible for use cases that orchestrate the workflows.
So they have distinct responsibilities. And within the domain project, developers face a really crucial design choice regarding the product entity. We must distinguish between a rich domain and an anemic domain.
Yes, that is a massive point in the book.
An anemic domain is simply a beta structure with public properties and absolutely zero logic. A rich domain, however, uses private setters for critical properties, such as a product's stock level.
Which is crucial for protecting the data.
Exactly. By making the setter private, the stock level can only be modified through controlled, dedicated methods that enforce the business rules. If an external service attempts to reduce the inventory below zero, the method natively rejects the operation.
That's a great explanation.
We can visualize an anemic domain as an empty shell, or maybe a simple wooden puppet. External service classes pull all the strings, manually manipulating the puppet's data. If the external service makes a mistake, the puppet just breaks.
I like that analogy.
Thanks. A rich domain, by contrast, is like a smart device. It knows how to operate itself safely. You can send it commands, but it will natively reject any invalid commands, ensuring its own internal state remains perfectly valid at all times.
Extending that visualization, a smart device reduces the burden on the user, just as a rich domain reduces the burden on the application layer.
That makes sense. It handles its own rules.
Right. And once the domain is established and capable of protecting its own state, we move outward to the application layer to construct our use cases. These are operations like add item to cart or process payment.
And because we maintain that inside-out mindset, we write these complex workflows before a database server is even provisioned, right?
Exactly. We validate this isolated logic using the XUnit testing framework and a library called nsubstitute. Nsubstitute allows us to create mock dependencies.
Oh, I've used that. It's incredibly helpful.
It really is. For instance, we can generate a fake interface for our inventory system that instantly returns a predefined value. This means our unit tests execute in mere milliseconds.
providing immediate feedback to the developer without the heavy overhead of network calls or slow database queries.
Exactly. Imagine how much time that saves an engineering team running thousands of tests on a Friday afternoon deployment.
It's game-changing. But, once our core business rules are locked down and heavily tested in isolation, we have to actually get data into the system without contaminating those rules. We must connect the infrastructure and persistence boundaries, enabling the application to finally interact with the outside world.
Right. And infrastructure implementations reside strictly in the outer rings of the architecture. Consider how our application communicates with external payment gateways. We manage these HTTP dependencies using a .NET library called refit.
Refit, paired with the HTTP client factory, correct?
Exactly. Instead of writing repetitive boilerplate code to manually open a network connection, serialize data into JSON, and handle all the HTTP headers, refit allows developers to simply define an interface with specific attributes.
That sounds so much cleaner.
It is. Refit then automatically generates the underlying HTTP calls at runtime. And to wire these powerful infrastructure services into our application pipeline, we utilize dependency injection.
Dependency injection,
Right.
the backbone of modern .NET.
Truly. In .NET, dependency injection lifetimes define exactly how long a service instance lives in the service memory. The framework provides 3 formal lifetimes: transient, scoped, and singleton.
To visualize these 3 memory lifetimes, imagine a busy, real-world restaurant kitchen.
Okay, I'm listening.
Transient services are like disposable paper towels. A completely new, fresh paper towel is provided every single time a chef reaches for one.
Oh, that's good.
Right. And scope services are like a wooden cutting board used for a single customer's order. The board is shared among the chefs while preparing that specific meal, but it is washed and cleared away immediately after the order is complete.
And singleton?
Singleton services are like the shared kitchen oven. There is only one oven. It is initialized when the restaurant opens, and every chef uses that exact same oven for the entire lifetime of the establishment.
Taking your cutting board analogy further, if we use a new cutting board for every single ingredient, which would be a transient lifetime, we waste immense resources and create absolute chaos.
We'd run out of cutting boards in 5 minutes.
Exactly. But if we share one cutting board across different customers' orders, a singleton lifetime, we risk catastrophic cross-contamination.
Oh, right. You don't want raw chicken on the salad board.
Precisely. And that illustrates why selecting the correct scope lifetime is critical for database transactions. We want a database connection to be shared across all operations within a single user's web request, and then properly disposed of when the request ends.
That makes perfect sense. And regarding data persistence, we utilize Entity Framework Core. However, the database remains a mere implementation detail. The DB context and the repositories act as strict boundaries.
Right, because the application layer only knows about the interface, while the infrastructure layer handles all the complex SQL generation.
Exactly. And to prevent database-specific structures, like foreign keys, from leaking into our pure business logic, we map our database models to our domain models using a tool called AutoMapper.
Which is fantastic for keeping those boundaries clean. And because this database logic is safely isolated in the infrastructure layer, we can test it robustly.
How exactly do we test that layer without making a mess?
Well, we perform integration testing by spinning up isolated temporary databases using Docker and test containers. We then use a specialized tool called Respawn.
Respawn, how does that work?
It intelligently wipes the data from the tables between test runs, resetting the state in a fraction of a second without the heavy penalty of dropping and recreating the entire database schema.
Wow, that saves a massive amount of time. So we have built this pristine, isolated core, and we have wired it to a database using secure boundaries. But frankly, none of that matters if a malicious actor can simply bypass our defenses through the front door.
Very true. Security is paramount.
He really must address the presentation layer and our cross-cutting security concerns.
Let's do it. The presentation layer for Project Odyssey is built with Blazor Server, and a common anti-pattern in modern .NET applications is dumping dozens of service registrations into a messy, disorganized program file.
Oh, I've seen some terrifying program files in my time.
We all have. To maintain explicit dependency flow, the authors recommend moving these registrations out of the program file and into a dedicated service composition root class. This modular approach keeps the application entry point clean.
That is much better. And what about user authentication?
For identity management, the application integrates Microsoft Entra External ID for authentication, paired with Blazor for modern user interface components. User identity must be verified at this outermost presentation boundary, preventing any unauthenticated network requests from ever touching the core application layer.
Right. Discussing advanced security concepts, the source text actually references the real-world Midnight Blizzard attack on Microsoft.
Yes, a very sobering example.
It is. In that scenario, state-sponsored threat actors exploited weak authentication mechanisms and leveraged hard-coded credentials to escalate privileges and access sensitive systems. To harden our application against similar vectors, we mandate multi-factor authentication.
Absolutely essential these days.
Yes, and more importantly, we completely eliminate hard-coded secrets from our source code. We move all configuration credentials, such as database passwords, into Azure Key Vault,
Right, and the application securely accesses this vault using managed identities.
meaning the application dynamically asks the cloud provider for temporary access tokens, ensuring no passwords ever exist in plain text. Finally, we implement structured logging using the Serilog library.
Right, but logging can introduce its own security risks.
Exactly. And I have to challenge this logging strategy, especially when dealing with enterprise systems. How are developers supposed to balance the absolute need for detailed audit logs, which are critical for troubleshooting a midnight system failure, against the strict legal requirements of obfuscating sensitive user data to maintain privacy?
It's a tough line to walk.
If we hide the data, we cannot debug the issue.
Resolving that friction is a complex engineering challenge for sure. The structured logging solution relies on scrubbing the data at the boundary immediately before it is written to the storage medium.
Okay, so before it even hits the log file.
Exactly. Using Serilog, developers configure specific destructuring policies. When the application logs an error, it captures the full object context. However, during the serialization process, the destructuring policy automatically identifies and masks sensitive properties, such as passwords, personal identification numbers, or credit card details.
That's incredibly smart. So the logs remain highly structured and searchable for the engineering team to diagnose failures, but they are fundamentally safe from accidental data leaks or compliance violations.
You get the best of both worlds.
Now, as our system grows, we inevitably encounter the heavy scaffolding required to maintain these rigid boundaries. The sheer number of interfaces, models, and request objects can really slow down feature development.
It's a common complaint with clean architecture.
Let us discuss how we optimize the architecture and prepare the system for long-term deployment.
To reduce the immense boilerplate code, we introduce a library called MediateR. Clean architecture naturally separates the code that requests an action from the code that executes it. MediateR acts as an in-memory message bus, routing commands and queries to their respective handlers without requiring the presentation layer to directly depend on the application layer.
Okay, I see. And we pair this with fluent validation to cleanly centralize our input validation rules, right?
Exactly.
Right.
Furthermore, we formalize our operations using command query responsibility segregation, commonly known as CQRS.
Ah, CQRS.
Yes. This pattern strictly separates operations that modify data, which are commands, from operations that merely read data, which are queries.
That keeps things very organized.
It does. And to further alleviate repetitive coding tasks, the authors introduce a custom package called Entity Access. This package allows developers to automatically generate generic request handlers for basic database operations.
So it writes the boring stuff for you.
Exactly, preventing teams from writing identical, create, read, update, and delete classes for every single new entity they introduce to the system.
Wait, hold on. If we are using a tool to automatically generate generic handlers for everything, aren't we just undoing all that strict intent-driven architecture we just spent the last 15 minutes building?
That is a very fair question.
If we make the data access generic, we lose the descriptive workflow-specific power of clean architecture entirely.
Recognizing that boundary is absolutely vital, we must clearly delineate between generic convenience and strict business necessity. Generic handlers are intended exclusively for standard, low-risk data access.
Can you give an example?
Sure, like fetching a list of categories for a product catalog, or maybe updating a user's display name. These are trivial operations. However, when dealing with rich business logic, such as a complex checkout workflow that requires verifying inventory across multiple warehouses, processing third-party payments, and triggering asynchronous shipping notifications.
You can't use a generic handler for that.
Exactly. You must completely exit the generic pipeline. For those critical operations, you retain highly customized, specific use case handlers to ensure the intent-driven nature of the architecture is preserved.
Okay, that makes me feel much better about it.
We also optimize our system utilizing structured composition. By leveraging the service-composition.net library, we encapsulate our foundational dependency configurations.
Which really proves the architecture's modularity. Because the core is completely decoupled, we can reuse the exact same application pipeline in a background console application alongside our primary Blazor web application, sharing the logic flawlessly.
It's beautiful when it all comes together like that.
It really is. With the system fully optimized, we face the final hurdle of deployment and monitoring in a live cloud environment.
Right. The deployment process targets Azure Web Apps, and operational readiness is paramount for production systems. We implement formal .NET health checks, which provide continuous status reports.
Allowing cloud load balancers to monitor whether our application is healthy or if it needs to be restarted.
Precisely. We also utilize OpenTelemetry, combined with the Aspire dashboard for deep local observability. This allows developers to visualize real-time metrics, logs, and distributed traces while actually building features.
That visibility is so important.
It is. In the production environment, this standardized telemetry data is exported directly to Azure Application Insights for centralized monitoring. And because we strictly maintained our clean boundaries, extending the application is incredibly smooth.
Right. If we need to process intensive background tasks, we can deploy Azure functions that reference our core application project, completely reusing our existing highly tested business logic without duplicating a single line of code.
Which is the dream.
Yeah.
However, teams must remain vigilant regarding architectural decay.
Oh, architectural drift. It happens to the best of us.
It does. As systems age and pressure mounts, developers often take shortcuts. Common signs of long-term architectural drift include bypassing use cases to call database repositories directly from the presentation layer,
A huge red flag.
or allowing database-specific attributes to leak into the pure core entities, and ultimately allowing the infrastructure tools to dictate the business rules.
We definitely want to avoid that. Well, this brings us to a forward-looking question for you, the listener, to explore on your own.
I'm intrigued.
If clean architecture is fundamentally about predicting what aspects of software will change and isolating them from what will stay stable, how will the exponential rise of AI-generated code affect these rigid boundaries?
Oh, that is a profound question.
Right. If an artificial intelligence agent can safely map and refactor a tightly coupled, tangled monolith in a matter of seconds, will clean architecture become even more important as a structured, predictable framework for AI to follow? Or will the concept of human-readable layered boundaries become entirely obsolete?
Some to think about for sure.
Definitely. We strongly recommend that you read the actual book, Clean Architecture with .NET, to fully master these implementations and explore the technical code examples in depth.
It's an excellent resource.
To our friends of the show, we encourage you to subscribe to the channel to continue exploring advanced engineering concepts with us. We formally wish you a great day.